Hello and welcome. Today I'll be talking about deuterium compared to plain hydrogen in some isotope infrared spectroscopic studies conducted at the University of Pittsburgh in the Chemistry 1430 laboratory. Just a quick rundown of what we'll be going over today. I'm going to start with an introduction with the research goals as well as my hypotheses for the experiment. Then we'll talk a little bit about some theory background information as well as the experimental methods, followed by the results and equation palooza, and then I'll wrap everything up with a quick conclusion. In this experiment, the mass effects on IR spectra were studied using HCl and DCl. Deuterium is a heavy isotope of hydrogen, twice the mass and twice the fun, if you will. We calculated molecular constants from these spectra, which will be discussed in a moment. Additionally, IR theory was reviewed, a new laboratory technique learned, and IR has numerous applications outside of academic research, in addition to different analytical and physical chemistry laboratories. Before the experiment was conducted, several hypotheses were formed, the first being that the value of R sub E, your equilibrium bond length, will be independent of the isotope of hydrogen present. This is because it should not be affected by the addition of a neutron in deuterium, as it does not affect the attraction or repulsion of the two atoms that are bonded together. The second hypothesis was that there will be uneven spacing between the P and the R branches of the vibration-rotation spectrum for both HCl and DCl. This is because as the J value changes, the corresponding wave number for the transition should not change by the same factor. Just a quick IR overview for you. So applying quantum mechanics to the harmonic oscillator gives quantized vibrational energies. This is shown by the top energy equation and the function that's U-shaped and symmetrical. So in this equation, there's equal spacing between your energy levels of HV sub E, where V sub E is just your harmonic frequency. For both of these functions, however, the lowest eigenvalue is V is equal to 0. It's actually non-zero, and this is called your 0-point energy, which is the residual vibrational energy at 0 Kelvin. Because of the rigid rotor model where the bond length is fixed as the molecule rotates, in addition to the bond length actually changing in this harmonic oscillator model, there must be anharmonicity considerations, and this is taken into account for by the Morse function, which is the other function present on the graph that is non-symmetrical. So within this graph, dE is your potential energy at infinite separation, and this starts at the bottom of the well, and then alpha determines the curvature of the potential of the well and reflects the vibrational frequency, and these are the variables that consider the anharmonicity that's present. A difference that you can see besides the shape of the function between the harmonic oscillator and the anharmonic oscillator is that the energy spacing for the Morse function decreases at higher values of V. And again, that's because of our anharmonicity considerations, where V sub E, X sub E is your anharmonicity constant. Another version of the energy equation for this that uses J, the variable D is the centrifugal distortion constant. In the Morse potential function, you can see both vibrational and rotational energy levels in these changes. You must have a change in your eigenvalue to have a change in your J value as well. Change from 0 to 1 of your eigenvalue is a fundamental transition, while 0 to 2 is an overtone transition. This change in energy for the second overtone will be slightly less than double that of the first overtone due to the decrease in energy spacing as V increases, mentioned with Morse potential. On the right, you can see that as V is increasing, J is changing as well. It can either increase or decrease, but staying the same is forbidden, and that corresponds to the Q branch. If J is decreasing by 1, gives a lower energy transition, and that is the P branch, while if J is increasing by 1, it's a greater energy transition, and that gives rise to the R branch. To wrap up our theory, we just have a bit of variable soup left. So beta sub E is your rotational constant. It's a measure of how a molecule responds to increase in rotational energy, and it's inversely proportional to inertia. D is the centrifugal distortion constant. You might remember this from the Morse potential energy diagram. And this measures the changing bond length in response to increasing rotational energy. This makes the rigid rotor approximation more realistic and helps to bring those rotational levels closer together for the higher energy states. Additionally, alpha does this as well. It's your coupling constant, it considers both vibrational and rotational energy, and it makes the rigid rotor also more accurate and aids in the accuracy of your rotational constant. V sub E is your harmonic frequency, and R sub E is your equilibrium bond length. So now that we've defined all the theory and all the variables we'll be looking for, calculating, and such, let's get into the experiment. The laboratory setup for this experiment consisted of the connection of a sealed IR cell with a rubber hose to a round bottom flask containing sodium chloride. To this round bottom, a mixture of deuterated sulfuric acid and protonated sulfuric acid were added in order to produce HCl and DCl gas that could then travel into the IR cell. Here is the IR spectra received from this experiment. The overtone and fundamental transitions are labeled. And these were identified by both intensity and knowledge of the fact that wave number is proportional to energy. DCl and HCl were then labeled because mass and wave number are inversely proportional. The R and P branches were labeled as well. Here we have a zoomed-in view of the DCl fundamental transition. You can see that there is uneven spacing between the P and the R branches. For P, as J decreases to the right, the spacing gets larger, and for R, as J increases to the left, the spacing decreases. This is due to deviation from the rigid rotor model. Thus, as J, your angular momentum, increases for R, the bond length is increasing from centrifugal distortion, and the resulting moment of inertia is different. Thus, the energy changes are different, which results in the decrease in spacing. For the P branch, as J decreases, the rotation is slowing down, and the bond isn't stretched as much, so this change in moment of inertia results in a larger spacing. Additionally, the rotovibrational coupling affects the spacing of the molecule, the spacing of the transitions. As the molecule vibrates more, the bond is stretching. For the R branch, notice that as energy is decreasing, the intensity increases and then drops down sharply. The opposite is true for the P branch. This overall curve trend is due to degeneracy from having multiple directions of spinning and can be modeled by a Boltzmann distribution, especially at higher temperatures. You can also see small peaks next to these larger peaks, which can be attributed to the chlorine-37 isotope rather than the chlorine-35 isotope, which gives the larger peaks. This is supported by mass and wave number being inversely proportional, and also due to the relative abundance of these isotopes, the intensity makes sense. So, once we identified the wave number at each of the larger peaks positions, we did a plot of transition number and wave number with a Linus polynomial regression, which is shown below. The polynomial regressions returned equations in the form shown in bold. These coefficients could then be plugged in to solve for the variables in the energy equations for the P and the R branch shown below. Here's a list of some of these values that we found. Further data analysis was performed to solve for more molecular constants, such as the anharmonicity and the harmonic frequency. So using V sub 0A, which is energy for the fundamental transitions, and V sub 0B, which is energy for the overtone transitions, these two equations were used to solve a system of equations to solve for the anharmonicity constant. Again, the polynomial regression coefficients were used then in these energy equations shown below for the P and the R branches to solve for these molecular constants. With the harmonic frequency in hand, we can calculate several other variables, such as D sub E and D sub O. D sub E, again, being the depth of the potential well, and this was solved for using the anharmonicity constant and harmonic frequency. D sub O is the bond energy and was solved using D sub E, and again, the same variables. Additionally, R sub E, the bond length, was solved for using the reduced mass and the vibrational constant. K could also be solved for, which is the force constant, using again the reduced mass and the harmonic frequency. The same method of calculation was then applied to the HCl fundamental transition, and the polynomial regression, zoomed in IR spectra, as well as a data table can be seen on the slide. Here is the data for the HCl overtone transition, as well as for the DCl overtone transition. A quick note for the data analysis for the overtone transitions is that a slightly different equations were used for the P and R branches corresponding to the polynomial regressions. Here we have a condensed version of the calculated constants from the IR spectra. Alpha sub E, your coupling constant, is dependent on bond length, so it should be independent of isotope. but is also dependent on vibrational energy, which is affected by your reduced mass. It's inversely proportional to the reduced mass. Thus, it makes sense for the HCl coupling constant to be greater than that of the DCl coupling constant. Additionally, beta sub E was calculated, and for DCl, it's approximately half of that of HCl, which makes sense as the value of beta is inversely proportional to the reduced mass. Additionally, D, the energy of the bond, was calculated, and it was found to be a similar value for both compounds. Here we have the last set of molecular constants calculated as well. To start, V sub E, our harmonic frequency, we see that DCl is lower than that of HCl, which makes sense because mass and harmonic frequency are inversely related. From that, our anharmonicity constant was calculated, again following the same trend. Okay, as well, force constant K can be thought of as a spring holding together the two atoms, and the bond length and electrostatics of a molecule are able to influence K, but as neither change, both isotopes should have the same force constant, and variation can be attributed to random or instrumentational error. Related to that is our equilibrium radius, R sub E. Again, approximately the same, and this makes sense because only the neutron is added. Bond characteristics like electronegativity of the atoms remains the same. With the data analysis done, both hypotheses were able to be accepted. The first one being bond length is independent from mass, as well as different spacing in the P and R branches. These were both discussed previously in this presentation. Another thing that was shown in this experiment was that the Morse potential energy spacing was confirmed through the calculation of the energy transitions of the overtone and fundamental transitions. The overtone was found to be less than 2 times that of the fundamental, which supports the energy spacing decreasing as your eigenvalue increases. Additionally, the variables found to be dependent on mass were the coupling and rotational constants and the harmonic frequency. These were inversely related to the mass of the isotope. One limitation of this experiment is that the overtone transition was much smaller intensity than that of the fundamental, and the effects of this could be seen in higher error values for the polynomial regression of the DCl overtone, which then propagated through to the variables calculated. However, overall, high-res IR is useful to understand the structure and properties of molecules. It provides information of bond energy, strength, and length, as well as vibrational and rotational constants discussed. We use this to understand the effects of isotopes on these factors, but it also has numerous applications outside of the laboratory, such as identification of substance composition, functional group determination, and even within forensic criminal analysis. Thank you for your time.